Reading quiz 29 is the second part of our Riemann sum venture, and we're going to take a look at what happens if we are dealing with more than just a finite number of rectangles. Sounds ominous. So let's start with some terminology, and some of this will be review. This reading has to do with Riemann sums, and this technique we will use to approximate the signed area between a function and the x-axis. And we're going to do more than approximate in just a minute. We're going to find the actual value. Signed area, if you'll remember, is area that depends on whether a function lies above or below the x-axis and depends on the direction we choose to integrate. So just a quick little summary. If we go forwards and our function is above the axis, we're going to get positive signed area. If we move backwards and our function is above the x-axis, then we're going to get negative signed area. Move forwards on our x-axis and our function is below, we're going to get a negative signed area. And then if we move backwards and below, then it's like a double negative, and we will get positive signed area. So always pay attention to what your upper limit and your lower limit is. We will also begin to use summation notation, which is a convenient way of writing our sums in easy form. We studied that when we were in pre-calculus. If you remember, it's got our lovely sigma here. It's a capital sigma. And we're going to say, with our index, we're going to go from j equals m to n of a sub j. And so that means start at a sub m, our lowest value, and go all the way up to a sub n, which is our highest index value. Just to review, so then the sigma stands for sum. The j is what's called our index of summation. M and n tell us that we're going to start out at the number m. We're going to keep on substituting successive integers and add up our terms until we get to a sub n. M is our lower limit, and n is our upper limit. Just as an example, the sum from k equals 1 to n of k squared would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And I think I meant to put a 5 there. Whoops. That sum is equal to 55. So before we go on, some useful summation theorems and formulas. All right, so the sum from k equals 1 to n of c times a sub k is equal to that constant times the sum of the a sub k. So in other words, we can pull out that constant as long as it does not depend on k. That'll be a very useful formula that we'll use in this particular reading quiz. The sum of two functions can be broken up, and we can break it up into the sum of one function plus the sum of another function. That will also be useful. We can do the same with subtraction. Our power sums, the sum from k equals 1 to n of k is n times n plus 1 over 2. Hopefully that's one that you studied in pre-calculus. If we want to sum the squared numbers, that sum from k equals 1 to n is n times n plus 1 times 2n plus 1 over 6. And the cubes would be n times n plus 1 over 2 all squared, looking very similar to the one for the sum of our integers. Now, so you're probably going to have to memorize these, at least for now. As after a while, these are the three that you will see most prominently, and you'll get to know them pretty well. So, example 1, where do we use this sigma notation? Well, we can apply this notation to the procedure of finding the area underneath a curve. For example, we want to find the area under the curve f of x equals x squared from 0 to 2 using a right Riemann sum. So this is a complicated process at times. After a while, you will see how quickly it can go, but I'm going to lead you through the steps to start. The first step, write out n intervals representing the width of each rectangle. So we're going to use n rectangles in this case on an interval from 0 to 2. So that'll mean that each rectangle, if it has equal width, which we're going to do here, each interval will be 2 over n units long. Width of the interval is 2 divided by the number of rectangles, which is n. So if you want to think about, remember before when we were doing Riemann sums with charts, when we had the charts, we had specific x values, and we went and we said, okay, we got the interval from 0 to 2, and we want to find the right endpoint there. And we have the interval from 2 to 3, and we want to find the right endpoint there, 3 to 5, and so on. Well, it's the same idea here, and sometimes it's helpful to write out what your intervals are going to look like. The intervals are 2 over n units long, okay? So the first interval will go from 0 to 2 over n. To get the next interval, we need to add another 2 over n, which would make us make the interval 2 over n to 4 over n. Then we've got 4 over n to 6 over n. If you're having trouble with this, imagine that n is equal to 100 rectangles. So what we're saying is the interval would be from 0 to 2 over 100, 2 over 100 to 4 over 100, 4 over 100 to 6 over 100, and so on, and we keep on going. So rectangle 1 would be from 0 to 2 over n, rectangle 2, 2 over n to 4 over n, rectangle 3, 4 over n to 6 over n, and then if we just say we want rectangle k, whatever k is, it could be 17, it could be 150, it could be however many rectangles as long as it's less than n. So the pattern that we notice is that the very right endpoint is going to be twice whatever rectangle we're on. So notice that we get 6 over n as our right endpoint here. Well, that's just 2 times 3. 2 times 2 is 4, and so on. So our right endpoint is 2 times k over n. Our left endpoint is 2 times k minus 1 quantity over n. All right? And so we could see that by saying, okay, well, the left endpoint of one rectangle is the right endpoint of the previous rectangle. So that's where the k minus 1 is. Find that previous rectangle value multiplied by 2 over n. So now that we have all this information, the next thing we want to do is to determine the appropriate endpoints of each rectangle, and then a general form for the endpoint of rectangle k. All right? So we did the hard work by figuring out what our intervals look like. There they are. The right endpoint for rectangle k is just going to be 2k over n. Remember what we mean by rectangle k is, if we wanted rectangle number 4, we would say, well, 2 times 4 divided by n, or 8 over n, would be that right endpoint. Then we need to find the width and the height of each rectangle. The width we already figured out. The width of each rectangle is going to be 2 over n. That was from the very beginning. And then the height of each rectangle, if you remember when we were doing our charts, the height of each rectangle can be found by plugging that endpoint, in this case the right endpoint, into the function. The function was x squared. So we're going to plug in 2k over n into x squared, and that's our height. And we remember width times height is equal to area of each rectangle. Our width, is the 2 over n, and the height is the 2k over n squared. So altogether, the area would be 2 over n times quantity 2k over n squared. Now, here's the real cool thing. When we're doing Riemann sums, now that we've abstracted a little bit, the summation formula and the summation symbol that we use is going to be able to help us add up all the rectangles. In this case, starting at k is equal to 1 and going to n. So we want the sum, the area of all the rectangles added together, because that will give us the total area underneath the curve. So that's the sum from k equals 1 to n of 2 over n times 2k over n squared. I kind of cleaned it up a little bit. That ends up being 8k squared over n cubed. And then we're going to do the sum from k equals 1 to n. The final part of it is we're going to evaluate it using our sigma notation. So remember our formulas we came up with for the sum of the integers and the sum of the squares and the sum of the cubes. Well, we're going to use those formulas noting that k is really our variable. K is what's changing in this problem. N is fixed. N is like we have 100 rectangles or we have 1,000,000 rectangles. All right? That's not going to change in this problem. It's the k that matters. So we can pull out everything that doesn't have a k in it. The 8 and the 1 over n cubed part. All right? And when we do that, we can simplify this and just have to worry about the sum from k equals 1 to n of k squared. That formula from before, from a previous slide, was n times n plus 1 times 2n plus 1 over 6. And that sum is going to be multiplied by 8 over n cubed. So the final kicker on this, the whole point of what we're doing is we've got all these rectangles. We could say n is any number that we want. N is 100, n is 1,000, n is 10,000, and so on. But what happens if we evaluate as the number of rectangles n goes to infinity? That's where our knowledge from a previous reading quiz number 2, comes in handy. If we do the limit as n goes to infinity, as the number of rectangles increases without bound, and our widths stay the same, and they get really tiny and really, really small, we get the limit as n goes to infinity of 8n times n plus 1 times 2n plus 1 all over 6n cubed. And if you remember, in order to evaluate this limit, we need to take a look at our highest powers in our numerator, which will be an n cubed, and our denominator, which will be an n cubed. Since those are the same, we just need to compare the ending coefficients, which is 8 times 2 on the top and 6 on the bottom, and our area is 8/3. That is an amazing statement. So what we're saying is the area under the curve, x squared, from 0 to 2 is equal to 8/3. No need to approximate, right? We have so many rectangles squeezed in that little area that we're going to be able to find the exact area, 8/3. It's done. That's the power of the limit. So some other quick terminology. We found the exact method for finding the area underneath the curve if we make the assumption that we get the area if we're to use an infinite number of rectangles. So to connect with the Riemann sum with what we just did with the finite definite integral, the definite integral on the left and the Riemann sum on the right represent the same idea. We're finding the signed area under the curve f of x from a to b. The connection is this sigma becomes the integral sign right here. The a and b aren't represented anywhere specifically in this particular formula, but they do show up when we try to find this delta x here, this change in x, which typically we keep as the same amount for each rectangle. And delta x is just the width of the interval, b minus a, over n. All right, so that part is what matches the dx part here. All right, that's our change in x. And of course, the function part matches with the function part here. So this limit right here is the definite integral here. It's just this is a little bit better of a format to use. Your calculator can assist in helping you find the value of the signed area underneath the curve. The button math number 9 uses an approximation to find the area. Depending on what type of calculator and whether you have pretty print and all that sort of stuff, use the following code. It'll come up and say fn int, and you type in the function. In our case, in this just example we just did, we would type in x squared. Our variable that we're integrating with respect to, that would be x. Our lower limit in this particular example was 0, and our upper limit, which was 2. All right, and there's a button I'll show you in class that will help when we're on the graphing screen. So just a quick little conversion here. Convert the given definite integral to a Riemann sum and then use math number 9 to evaluate. Let's say we have the definite integral from -2 to 3 of 4x dx. The width of each of the rectangles will be 5 over n. Well, that's 3 minus -2. That's the width of the entire interval. And we're going to divide by n for n rectangles. Our right endpoint is going to start at -2, and then it's going to add 5 over n each time. So like the previous example, it's going to add 5 over n, and when we want to get to the k endpoint, we would have added 5 over nk times, which we would write as 5k over n. So remember, we start at -2, it's like a shift, and then we're going to add 5k over n. Our height will be what we get when we plug in our right endpoint into the function. Our function is 4x, so we plug in 4, and we multiply it by, we plug in our right endpoint and multiply it by 4, so we get 4 times -2 plus 5k over n. And then to put it all together, our Riemann sum with the limit, the sum from k equals 1 to n of 4 times -2 plus 5k over n. This is our height, multiplied by our width, which is 5 over n, and then we're going to do the limit as n goes to infinity. Now, you didn't need to know that necessarily to plug that into your math number 9. It's just a matter of trying to recognize how these two are related to each other. Notice the 4 times x is our right endpoint, and then our width of our interval is 5 over n. That's our dx part. And if we go to math number 9, we get the value of 10.